Windows not coming. Okay, very good morning to all of you. There we are.
Morning.
Are you able to hear me? Hello?
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
There we are on to the Department of Chemical Engineering, Banastali Vidyapeeth, PhD 305 Chemical Technology. We are on lecture number 3. In the last lecture, we had a quick glance of India's expanding chemical industry. It was an article which had come in the American Institute of Chemical Engineering Journal, AICHE Journal, and it gave a nice coverage of the importance of the chemical industry in the Indian economy and the import-export, the scenario, the special focus on petrochemicals, and also it talked about what are the feedstocks options that are available for the industry like naphtha, biomass, etc. And that's where we were discussing this. In the last lecture, we stopped at agrochemicals, how they play a role. So there we take off from that point now, agrochemicals. You know, agriculture is critical to the Indian economy, and the farmers are agitating. You are all aware of it, right? So agriculture is a very important part of Indian economy and the food security of the billion population, and it accounts for 15% of the gross value added, right? 60% of the rural households rely on farming for their livelihood. And any industry has to support the agriculture, is obvious. Indian agriculture faces many challenges and must face to adopt to doing more with less. That is, we should improve our per acre yield, which is for most crops less than that of many other countries. So we are producing, but our per acre growth of or per hectare growth of say rice, paddy, and many crops, they are far less as compared to several other countries. We are a growing population, urbanization and industrialization, and more apartments coming. Farmlands are decreasing, shrinking, and the population with a lot of money, affluent population, is demanding, more land, more houses, multi-story complexes, whatnot, right? Even rural India is, into building boom, right? Water availability for irrigation has become a source of contention, and, there are a lot of inter-water river dispute, Karnataka and Tamil Nadu for the Kaveri water, and several other states, right? Andhra Pradesh, Telangana, etc. Right? There are many disputes with neighboring countries as well as with between states. India also has a lot of water sharing with Pakistan and China, and there are a lot of disputes in the water sharing agreement. Groundwater depletion has reached alarming level, and the states were forefront of green revolution like Tamil Nadu, Punjab, etc. They are all having what is that severe groundwater depletion, right? So India, of course, the states like Punjab and Tamil Nadu with the green revolution turned India from a beggar of food to an exporter of food. I mean, during 60s, India was so bad in food crops. We were importing, and the scene was very bad. And today, we export to the same countries from where we imported in 60s. Okay, increasing agricultural productivity is important. Why we are discussing is for doing all these things, chemical industry has a role. Increasing agricultural productivity means say better fertilizers and better pesticides, etc. Right, and consolidation will yield economics of scale, mechanized farming, and wider adoption of high-yielding seeds, including those genetically modified. The BT cotton, genetically modified cotton, right? Better nutrition management, including balanced fertilizer use, more efficient water management, integrated pest management, IPM, and combining chemical and biological approaches will also be beneficial. That is about the stakes of chemical industry for the agricultural sector. Unlike other agro-based economies, India is fortunate to have a vibrant agrochemical industry. Our agrochemical industry is the fourth largest in the world after the US, Japan, and China. And the industry produces mostly generic off-patent product for the local market and increasingly for export. And India has become a dominant producer of products such as synthetic pyrethroids and uh, proturon, right? Pesticides which don't use phosgene. Phosgene is a very poisonous gas. In 2015-16, the agrochemical industry's output was valued at about US dollars 4.3 billion, divided roughly equally between domestic sales and exports. That means a good division between exports and domestic, consumption. The overall market is expected to grow 10 to 12% annually to about US dollars 7 billion by 2019. We have to see whether we have achieved it or not. Exports are expected to grow faster, 12 to 14% compound annual growth rate, CAGR, than the domestic market. So exports are expected to shoot ahead of the domestic market. Domestic market is in the 7 to 9% growth rate, whereas exports are in the growth rate of 12 to 14%. India's agrochemical industry has made considerable progress. It does have vulnerabilities. The market is skewed towards insecticides, which is not surprising given India's tropical climate. A lot of insects happen. Fungicides and herbicides share small portion. Insecticides are a major consumer, are majorly consumed in the Indian agriculture. Distribution, however, is slowly becoming more balanced. Okay, the introduction of pest-resistant genetically modified cotton, BT cotton. As you know, a lot of farmers in Maharashtra and several states used to commit suicide because of the cotton crop getting lost due to pest attack. And pest-resistant genetically modified cotton, BT cotton, dramatically reduced the insecticide use but did not eliminate it. It only reduced the consumption of insecticide but did not eliminate it. The evolution of agricultural basket is a large proportion of horticultural products. Horticultural products are fruits and vegetables at the expense of food grains and cotton is increasing the fungicide use. So with India focusing more on fruits and vegetables, more fungicides are coming into picture. A labor shortage, surprising for such a populous country, is not everybody is willing to go to agriculture, right? So is driving a greater herbicide use as a mechanical weed removal gives way to chemical approaches. Earlier, unwanted plants in the field used to be plucked manually and chucked out, but more people not getting into agriculture, you have to use mechanical weed removal. Then what is this? So slowly, chemicals are coming into picture as herbicides, weedicides, fungicides, etc. Okay, much of the industry is focused on making and marketing older generation products that could be edged out by newer patented products that are more efficacious, targeted, and safer for human health and environment. Indian agrochemical companies are not likely to invest in research for new molecules given the limitations posed by individual and collective size. Remember, the Bhopal accident was the plant making insecticide, pesticides, etc. Right. So they are highly, harmful chemicals, and slightest carelessness could lead to serious accident and cause death. Okay. Continued human company successes will hinge on their ability to adopt to one of the four business strategies: going global. Right. Our agriculture must go global, forging marketing alliances with the international partners, entering into toll and contract manufacturing arrangement. Some of you, if you are reading, the new farm policy is talking about this contract manufacturing arrangements, etc., focusing on formulation development, newer molecules and chemicals for insecticides, pesticides. Several companies are already adopting one or more of these approaches. The agrochemical business is changing dramatically. The industry is viewed holistically with a portfolio of seed and biotech capabilities that complement the traditional chemical business. The global business landscape is also undergoing. Remember, the Dow DuPont merger, one of the biggest things to happen in the industry. Dow was a top 10 chemical manufacturer. DuPont was also a top 10 chemical manufacturer. When both of them merged, they landed up with a huge giant, Dow DuPont, and now it's known as only DuPont, right? And Chem China's acquisition of Syngenta and Bayer's purchase of Monsanto, these all have put, some very big companies in the picture, global level organizations, and these dynamics will play out directly in the Indian market where all of the multinationals have a presence. Remember, DuPont, Bayer, BASF, all are there, in the Indian scenario where all the multinationals have a presence. They could also impact existing relationships with Indian vendors and force realignment of marketing strategies. So a lot of business tactics are going to happen in the agrochemical industry in terms of fertilizers, pesticides, herbicides, fungicides, weedicides, etc. Okay. Then coming to education and research, no development of industry, especially the chemical industry, can be achieved without proper education and research, right? The specialty chemical sector is capital and operating expenditures are comparable and in some cases lower than global standards. So we do have advantage in case of specialty chemicals. I told you India is already on the rise in the global scenario for making specialty chemicals. Cost can be reduced by as much as 50% via process intensification techniques. This is something we are going to study in the course toward the end, which could also increase production to US dollars 100 billion per year. That's a huge thing to achieve. Okay, and India has adequate research and education infrastructure to support process intensification work. We have 90,000 masters, MTech students, 6,000 PhD chemistry graduates, 1,000 masters, and 300 PhD chemical engineering graduates each year. Okay, so both, you have from chemistry and chemical engineering, sufficient number of people coming out, and considerable work is still needed to generate the appropriate skills to meet the needs of specialty chemicals manufacturing and research. I already told you that among the women universities in India, Banastali Vidyapeeth is the only one which is offering chemical engineering at the bachelor's level for women. To complete our discussion of the Indian chemical industry, there is a broad consensus that India can achieve and maintain 7% GDP growth rate for reasonable period of time. But right now, the year has been bad because of the pandemic, COVID, Corona, all those confusion, right? So the GDP is badly affected, but India's potential for 7% GDP growth is undeniable. The Confederation of Indian Industry, CII, which is the apex body of Indian industry, has set a target to triple the size of the Indian chemical industry between 2015 and 2025, which, if achieved, will take the industry to US dollars 430 billion by 2025. India will be a major name to reckon with in the chemical industry in the global scenario. This ambitious target will not be achieved if business runs as usual. Business will require a coordinated blend of policy interventions at the macro and micro level. Macro means national level, micro means at the company level, and company level initiatives plus greater international market access. The industry will need to recognize the paradigm shift in technology and markets that will have consequences for Indian companies. In fine chemicals, these are, remember, fine chemicals are those, which are made in small volume but large price, right? Small volume and large price. Fine chemicals is a part of specialty chemicals. Okay, so most of the fine chemicals are made as batch processes. You know the difference between batch and continuous process, right? And the fine chemicals are more in the batch processing technique, and slowly they are transition from batch to continuous is underway, which means that India will produce huge quantities of specialty chemicals, right? And the fine chemicals, offering the benefits of safety, quality, scale, and investment. Remember, bulk chemicals or commodity chemicals are those which are made in large volume and they command less price. Whereas fine chemicals and specialty chemicals are made in small volume but they command a high market price. That is the difference. Okay, the last lecture we had seen it. The recent replacement of multiple indirect taxes by single goods and service tax. So Indian industry had a problem paying multiple taxes of all kinds, which has all been simplified with the introduction of GST, goods and service tax. GST will positively impact manufacturing, and with long value chain, the chemical industry will be a significant beneficiary as taxes impact pricing of products and services, supply chain optimization, IT, accounting, and tax compliance system. So GST is going to play a big role in a better performance of the chemical industry. The chemical industry will continue to be dependent upon oil and gas for the near future, but it is prudent to look at alternative feedstock. Biomass and coal come to mind, and a more comprehensive and coordinated approach is needed to exploit both. So the alternative for oil and gas is biomass and coal. India has good amount of coal, not of a very high quality, but high quantity is there. India has a thriving alcohol-based chemicals industry that was decimated by the diversion of ethanol as a gasoline additive, right? And coming back to alcohol-based chemicals from the agricultural sector is not ruled out. Coal is making a comeback for fertilizer production, and right now, fertilizer production is more using natural gas, naphtha, or fuel oil, but coal is also a viable alternative, and using it for chemicals such as methanol, olefin, and derivatives, which seem to have worked well in China. They need to be carefully evaluated in the Indian context. So, enter the coal back. Okay, integrated gasification combined cycle, IGCC plan to burn even low-grade coal efficiently and cleanly for power generation need to be pursued further. Right, low-grade coal means ash content is quite high. Indian coal is mostly low-grade, having 40 to 50% ash content. Unlike many other countries with significant chemical industries, India still lacks a national inventory that identifies chemicals in commerce and the risks and hazards they possess in their value chains. So accidents keep taking place in terms of production and storage, and this should become a priority project with clear timelines for phasing out of harmful products, especially the ozone depleting chemicals. India has done a big way to get rid of them, and the support for innovation of safer substitutes. Okay, so removing chemicals which cause harm to the environment and replacing them with more environment friendly. That is the green approach. And the industry will also have to decouple the past growth model and re-examine available opportunities. Many leading global companies are re-evaluating their portfolios through the lens of sustainability. Sustainability means without damaging the environment to the extent possible. And these are lessons for Indian companies. Okay, India has a proven track record of entrepreneurship. The country also has some strengths in technology development that have not been fully leveraged, and chemical and women entrepreneurs are a rising force, and we expect that a good number of girls from Banastri also become entrepreneurs in the chemical sector. Okay, the chemical industry has a long way to go in forging intercompany and academic partnerships to drive innovation, although some pharmaceutical companies have nurtured to meet their business requirement. Of course, long-term research is still lacking, and even companies that like to be counted in global ranking have only made very little forays into research activities, R&D. India must make wise investment choices, and fine and specialty chemicals, the future for India hold particular promise because they don't expose the economy's weakness, high cost of capital and lack of access to hydrocarbon and high energy cost while leveraging strength. We have high technical skills and low cost innovation capabilities. So we are at a positive when it comes to these aspects. Okay, developing a fine and specialty chemical business will provide significant opportunities for Indian chemical companies. However, the business will not thrive without a backing of robust and broad-based industry. Finally, industry must have access to enough workers with the right skill sets and motivation. And given the industry's poor image among the country's youth, not everybody is willing to become chemical engineers. Even boys, among the girls, they prefer IT and electronics. So people think that chemical industry is a dirty industry and they don't want to work in a dirty industry. This attitude must change, and chemical industry is as challenging as any of the other industries. So the literature that was used in doing this article is here. Any of you interested in reading more could go through these references that are given. Okay, so let me not this is only for more reading from your side, depending upon, see, somebody wants to see chemicals and petrochemical manufacturers, this reference will give you, right, a naphtha for petrochemicals, Confederation of CIA, Indian Industry, CII report, the famous cutout committee report for active pharmaceutical ingredients, API, right, and so the GST, so many of these articles will throw more light on what we have discussed in this lecture. Now, let's come back to our business process. Okay, so they just restating what we already know. You know, process, the defined as the engineered sequence of physical, chemical, mechanical transformations which convert a readily available raw material into a useful product with optimum utilization of resources deployed. The most economic fashion or the most optimum fashion. We have to convert the raw material into product, and we prefer the raw material is readily available and the product is useful. And to convert raw material to product, I have to do physical changes, chemical changes, and mechanical changes to do the desired goal. Chemical transformation form the backbone of any process around which physical and mechanical transformations are built. Remember, if there is no reaction, then there is no fun. There must be a reaction, and around that reaction, we build the physical and mechanical transformation to develop the technology. So, the chemical transformation form the backbone of any process technology, and it is around the chemical transformation, the physical and mechanical transformation are built upon. Okay, so first and foremost thing is one must make sure that the reaction can be carried out or not. To do that, you carry out detailed literature survey to see the research activities and see whether a reaction can take place or not, and bench scale laboratory equipment. Bench scale means in the lab scale, test tube, beakers, and round bottom flasks and whatnot. Right, bench scale to see if a reaction can take place. Right. And now remember, when you say a reaction can take place, we desire to carry out the reaction at ambient conditions. What is ambient condition? Atmospheric pressure and room temperature. Why? Why do we want to do at atmospheric pressure and room temperature? These are itcha, desire. Because we don't have to spend any money. Right? The atmospheric pressure and room temperature is available as it is. So I don't have to spend money to achieve a desired pressure or temperature. So doing a reaction at ambient condition is the most desirable thing. Not every reaction is ready to undergo at atmospheric pressure and room temperature. Why? So now you know why we want to do it. So what problem we face? For any chemical reaction to take place, there are two aspects which are important. What are the two things? One is the thermodynamics, which dictates the equilibrium conditions. Remember, thermodynamics tells the equilibrium part of the reaction, and kinetics tells the rate of the reaction. So thermodynamics and kinetics will determine whether a reaction can take place or not. There may be a reaction which is thermodynamically favorable, but the kinetic does not allow. Right? So if that is, the rate is too poor, rate is too slow for any meaningful reaction to take place. Rate is poor. Okay. Now, I told you that our most desirable thing is we want the reaction to take place in ambient condition, even though equilibrium is favorable. But suppose it doesn't take place at atmospheric ambient conditions, then what do? We try the reaction, keeping the pressure atmospheric, but we will try the reaction at different temperatures. Right? So it is not taking room temperature means what? Say 25 degrees. Right? So try 35, 45, 55, 65. Right? So try a different temperature range, the reaction. It is possible that in some temperature range, the rate becomes favorable, that is, the kinetic comes into action, and you have got the reaction which will take place at atmospheric pressure and at a higher temperature. If that does not work, suppose that various temperature ranges also, you find that the rate is not favorable. Right? Equilibrium is favorable, but rate is not favorable. Then if rate is not favorable, then look for a catalyst. Okay. So we will try different catalysts. You know the role of catalyst. Catalyst does not take part in the reaction, but it ensures that the reaction is enhanced. Okay, so facilitate the reaction for increasing the rate of the reaction. Okay, so the first strategy is try to do the reaction at ambient condition. If not, keep pressure atmospheric and try at different temperatures. If that works, cool. Even if at different temperatures the reaction does not take place, look for a catalyst. Right? So it's possible that with a catalyst you are able to reach the desired reaction rate. But let's say if with the catalyst you try so many catalysts, but it is still unfavorable. Right? So then you find that at atmospheric pressure, at different temperatures, the reaction does not work. At atmospheric pressure, different temperatures and various catalysts, the reaction does not work. Then you give a brand to it. It is an unfavorable reaction. If that does not work, then the reaction is unfavorable. Now, how do we unfavorable doesn't mean we give up. Temperature, pressure catalyst. It can undergo only with electrolysis. Put the salt solution in a cathode anode electrolyte itself, pass electric current, and the brine solution dissociates, and then you form caustic soda and chlorine, right? So, as the product. So, electrolysis. Another example is zinc sulfate to zinc. It's got by electrolysis. जो हिंदुस्तान जिंक चित्तौड़गढ़ में नजर डाल रहे हैं for internship. Remember, electrolysis, zinc sulfate to zinc is one of the major action there, electrolysis. Then comes high pressure. Classic example is ammonia. Nitrogen and hydrogen will not combine with at room temperature and pressure, even at increased temperatures, even with catalyst. So the only way by which nitrogen and hydrogen combine to form ammonia is N2 plus 3H2 form 2 ammonia, famous reaction. Haber-Bosch got their Nobel Prize for it. Okay, so you use iron catalyst and pressures of the order of about 200 to 300 atmospheres is required. So you know the famous Lee catalyst principle. If an equilibrium is disturbed, the reaction will adjust to restore the equilibrium. So by increasing the pressure, I am disturbing the equilibrium of the nitrogen hydrogen to form ammonia reaction, and the system will now adjust to move to the right. So that is why at high pressure you will find that nitrogen and hydrogen in the presence of iron catalyst combine to form ammonia. In fact, if you lower the pressure, ammonia is capable of dissociating back into nitrogen and hydrogen, right? So high pressure. Then low pressure. Low pressure is, remember, as a thumb rule, whenever there is an increase in number of moles in a gaseous reaction, remember ammonia manufacture, recall the reaction, N2 plus 3H2 forms 2 ammonia, right? N2 plus 3H2 forms 2 ammonia. How many moles are there on the raw material side? N2 1, 3H2 3. 3 plus 1, 4 moles of raw material. How much product is formed? 2 moles of ammonia. So 4 moles on raw material side, 2 moles on the product side. So whenever there is a decrease in number of moles in a gaseous reaction, you will find that high pressure will favor the reaction. The reverse will come for low pressure, right? Whenever there is a increase in number of moles as compared to raw material, then low pressure will favor the equilibrium. Example is cracking of hydrocarbon. Like naphtha is a long chain hydrocarbon, and one at low pressure, you will find that this hydrocarbon can crack into smaller hydrocarbon. That is, I can do the cracking either by heat, thermal cracking, or using a catalyst known as catalytic cracking, or simply cat cracking, right? So a long chain hydrocarbon is broken into many small chain hydrocarbon. For example, if I crack naphtha, the output of the naphtha cracker will be, say, methane, ethane, ethylene, propylene, and butane, like that, right? So for that, the number of moles of product is more than the number of moles of the raw material. So in which case, low pressure will favor, right? And there are two techniques for achieving low pressure. One is the put a vacuum pump, right? So it will cause lower pressure. right? So when you evacuate, the pressure drops falling and you reach vacuum condition. That is how you reach low pressure. Yet another way of achieving low pressure is add a inert material to the mixture so that the partial pressure will be reduced. Remember, if I crack naphtha, then it forms product. But I make naphtha with steam. Now, steam acts as an inert for me. Steam does not mix with naphtha, so the total pressure is now lower on naphtha because the total pressure is shared by the raw material and the inert, right? So adding a inert is another way of bringing low pressure because the partial pressure on various species will be reduced. Then comes reaction coupling. Remember, iron oxide, most of the ores are found as oxides, copper oxide, iron oxide, zinc oxide, etc. And iron oxide will not become iron and oxygen. Right? If it can become, then iron oxide would not have been formed. Right? Iron oxide, as per Pandas you would have studied in structure and properties of material, iron oxide is a stable form. That is why it exists. Right? But breaking into iron and oxygen does not work. But how do we then get iron from the iron ore? Then I do reaction coupling. This is very interesting. Reaction coupling is I have one unfavorable reaction. You know, Gibbs free energy. If delta G is positive, the reaction is not favorable. If delta G, Gibbs free energy change is negative, then the reaction is possible. So in reaction coupling, I simultaneously mix one unfavorable reaction with a favorable reaction so that combination will work, right? So I couple unfavorable reaction with a favorable reaction. Remember, iron oxide forming iron and oxygen is unfavorable. Delta G is positive. But carbon combining with oxygen to form carbon monoxide is highly favorable. That is why in the metallurgical industry, we use coke. The C is not coal, it is coke, pure carbon, right? So carbon is readily combined with oxygen to form carbon monoxide, which is a highly favorable reaction with delta G negative, right? Whereas iron oxide forming iron and oxygen, FeO dissociating into Fe plus half O2, it doesn't happen, right? That is unfavorable. But carbon with oxygen forming carbon monoxide is favorable. Now, when I do both the reactions simultaneously, the energy released by the unfavorable reaction will get sucked in by the unfavorable reaction. Energy released by the favorable reaction will be picked up by the unfavorable reaction so that that can also take place. That is why you get the final output as iron and carbon dioxide because carbon monoxide will combine with more oxygen to form carbon dioxide. So reaction coupling, very interesting. Then comes the classic Solvay process, right, for making sodium carbonate, right? Sodium carbonate, remember it contains sodium and carbonate. The sodium containing material which is available in plenty is sodium chloride. See, by looking at the product, you should be able to determine the raw material, right? So product has sodium, which means the sodium most likely should have come from sodium chloride. Carbonate, calcium carbonate, limestone is very abundantly available on earth. So carbonate should have come from calcium carbonate. So the raw material NaCl and calcium carbonate forming Na2CO3 plus I think this equation is wrong. Please get it corrected. This should be calcium chloride, right? CaCl2, not CaCO3. It should be sodium carbonate and calcium chloride. I'm sorry for this typing mistake. So it should be calcium chloride. Okay. Please make the correction. Okay. So remember, this reaction does not go by electrolysis, high pressure, low pressure reaction coupling. It is a roundabout way. Sodium chloride is ammoniated. Ammonia comes in looking like a catalyst, but by definition of catalyst, catalyst does not take part in the reaction. But in this case, ammonia comes into picture, the brine gets ammoniated, then comes carbonated carbon dioxide, and then, ammonium bicarbonate is formed, then which is converted into sodium bicarbonate, and sodium bicarbonate will, on heating, gives you sodium carbonate, and ammonia there is regenerated. So we have done this Solvay process in the chemical process calculation, and of course we will be seeing it in the chloralkali industry also. But please make the correction here. This is calcium chloride. Okay, sorry. Now come to unit processes in chemical process industries. Remember, chemical reactions are the core of heart of the chemical technology. The chemical technology is a combination of unit processes and unit operation. Unit processes involve chemical conversion leading to synthesis of various useful products and provide basic information regarding at what temperature the reaction takes place, at what pressure, what is the extent of chemical reaction. Oh, remember all those heat, right? Extent of reaction which you had studied in the chemical process calculation. That is the extent of reaction eta, yield of product, product of reaction nature, nature of reaction, and whether endothermic or exothermic, type of catalyst used. All this evolves by the unit process or the chemical transformation. And unit operations involve physical separation, right? Like heating, cooling, distillation, all these are unit operation. Okay, now let's have a look at some of the unit processes which are of importance to the chemical technologies. So this is there. We will just run through it to get a idea of the important chemical reaction. Alkylation is there in the petroleum refining industry. Alkylation is adding alkene to an alkane, right? Typically a isoalkane. So the alkene is one butylene. It is added to isobutane. The product is the ethylene, the alkene plus alkane, isoalkane. It forms 2,2,4-trimethyl pentane or isooctane, right? So remember, octane number. So if you want to increase the octane number of the petrol your refinery is making, then it's better to have one alkylation unit as part of the refinery, right? Because as part of the refinery, some butylene will be produced, and this butylene with isobutane can be used for forming this. So this is alkylation. It is we'll be studying it in the petroleum refining industry. Then come amination by ammonolysis, right? Ammonolysis means ammonia, right? Look at this reaction, ethylene dichloride. Ethylene dichloride, ethylene with one chlorine on both sides of the double bond. C2H4, so you have added a chlorine on both sides to saturate it, right? So ethylene dichloride with ammonia forms ethylene diamine. This is used for making dyestuffs, coloring chemicals, dyestuffs, organic chemicals, synthetic fibers, ethylene diamine, right? So this is a very classic reaction. Then you have adipic acid plus ammonia form adiponitride, right? So you can see that what the ammonia is entering, right, and knocking out something. The oxygen is gone now. Okay, adipic acid forming. This is the CO2H means COOH. Okay, so adiponitrile. Ammonia enters into adipic acid, and I think a water molecule will be eliminated. Okay, adipic acid to adiponitrile. Then come amination by reduction. See, nitroparaffin, right? So paraffin means, straight chain hydrocarbon, right? Saturated hydrocarbon, and nitro. There is a nitro group, NO2 here, right? So 2-nitroparaffin, this can form isopropylamine, right? So this is amination by reduction. Okay. See, in the earlier case, amino lysis, ammonia is breaking, right, to combine with other chemical. Here, ammonia, what is this happening here? Amination by reduction. Amination by reduction is, see what's happening. CH3, CH, NO2, CH3, H2. So the oxygen is getting out and the hydrogen is entering. So CH3, CH, so NH2, so instead of oxygen, hydrogen has come in and oxygen combines with the remaining hydrogen to form water. Okay, so nitroparaffin to form isopropylamine. Then comes ammono oxidation. Right. So ammono oxidation is propylene plus ammonia plus air. Right. Form acrylonitrile. This is used in the plastics and synthetic fiber. Making of acrylonitrile, I think I mentioned in the previous lecture somewhere, the Sohio process, SOHIO. Sohio process is widely used. We will be studying it in the petrochemicals when we reach there. Then comes this important reaction, calcination. See, this lecture we are just looking at some of the famous reaction which will come somewhere in our study in the remaining part of the semester. Okay, calcination. Therefore, the cement making limestone, calcium carbonate on heating becomes calcium oxide plus carbon dioxide. And this reaction is very important for cement manufacture because then the calcium oxide will combine with silica to form disilicate, trisilicates, etc. Okay, so calcination is the heating of calcium carbonate to form calcium oxide and carbon dioxide. Then comes carbonylation. Methanol plus carbon monoxide form acetic acid. Right? Methanol and carbon monoxide forming acetic acid is a very interesting reaction. Then comes carboxylation. So this is benzene ONA. This is a, I think it's a sodium phenoxide, right? So under pressure, it will form, that is this, it become COONA. Okay, so this is also used for organic chemicals. Combustion, hydrocarbon combining with oxygen to form carbon dioxide and water, right? Very widely used. Any fuel, here the fuel is hydrocarbon methane reacting with oxygen to form carbon dioxide and water, combustion, process heating. Then comes condensation. Condensation is typically the elimination of a water molecule where OH from one material and H from another material will combine to form water. So you can see the example here, benzaldehyde plus acetaldehyde forms cinnamaldehyde plus water. So what has happened is, so here you have the OH, one hydrogen and OH combined to form water, right? So that leaves us with cinnamaldehyde, and this is done with caustic soda as a catalyst. Okay. Then comes phthalic anhydride. Phthalic anhydride plus benzene. This becomes anthraquinone. So this is used for organic chemicals and dyestuffs, and this condensation reaction is used in synthetic perfume. Then comes cracking of polymers. Cracking means port dalo, a long chain hydrocarbon. Look how many chains. Carbon 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. So a 7 carbon is broken into 3 carbon, one product, and 4 carbon, another product. Right. So we have broken a 7 carbon chain into one smaller chain with 3 carbon and one bigger chain with 4 carbon. So cracking or pyrolysis. See, there is a difference between cracking, pyrolysis and oxidation. In the case of combustion, remember there is some oxygen coming in. Whereas here, in cracking, there is no oxygen coming in the picture. Right? So, hydrocarbon just smashes into uh, smaller hydrocarbon. A larger hydrocarbon becoming smaller hydrocarbon. Okay. Then comes cyanidation or cyanation. You can see acetylene plus HCN form acrylonitrile. Of course, we just saw that there is another alternate route for acrylonitrile, propylene plus ammonia with air forming acrylonitrile. Of course, this is also there, but this is not very popular because of HCN coming. HCN is a, poisonous gas, right? So it is not widely used. Then comes cyclization. What is cyclization? Like N-hexane forming cyclohexane. Normal hexane, C6H18. Cyclization is N-paraffin forming a cyclic compound. That is by dehydrogenation. So by removing hydrogen, you are forming a cyclic compound. So this is why this is also used in the petroleum industry. This is known as the reforming reaction, where straight chain hydrocarbon becomes cyclic. The cyclic hydrocarbon is also called naphthenic, right? And further dehydrogenation will convert a cyclohexane into benzene, right? So paraffin to naphthene to aromatic is done by cyclization. I think the catalyst used is platinum. So this is known as reforming. That is why this reaction is known as the reforming reaction. This also forms a part of the petroleum refinery. Then comes dehydration. Dehydration is removal of molecule of water. Ethyl alcohol plus ethylene forms, ethyl alcohol can form ethylene and water. So when water is eliminated, you are left with ethylene. Calcium hydroxide forming calcium oxide and water. This is also dehydration reaction. That is the water is removed, dehydrate. Then comes dehydrogenation. Dehydration is removal of water. Dehydrogenation is removal of hydrogen. 1-butene becoming 1,3-butadiene with hydrogen dehydrogenation. So when you remove a hydrogen from butene, it becomes butadiene. Butadiene, remember, is a very important chemical for making synthetic rubber. So when butadiene is mixed with styrene, you form styrene butadiene polymer rubber. Right? Diazotization and coupling, the synthetic rubber. Diazotization and coupling is used in the dyestuff industry. Or NH2, or could be anything. CH3, C2H5, any R could be anything. Alkyl group with NH2, with RNH2 plus HCl plus HNO2 forms the nitrous acid. This forms RN2Cl plus 2H2O. And this is an important reaction for making dyestuffs. RnCl, this is this, right? Rn2Cl plus this hydrogen, this chemical forms RNR. This is a dyestuff. Okay. Then comes disproportionation. What is disproportionation? Propylene becoming ethylene and butylene. Remember, propylene is 3 carbon. 1, 2, 3. We are taking 2 molecules of propylene, which means there are 6 carbon on the raw material side. And what is there in the product? Ethylene, 2 carbon, and butylene, 4 carbon. So, 2 propylene forming ethylene plus butylene is known as disproportionation. Because why it is disproportionate? Butylene is 4 carbon, ethylene is 2 carbon. So, a 6 carbon is broken into 2 plus 4. This is very much there in the organic chemical manufacture. Then comes the double decomposition. You have studied this in the school also. Double decomposition. Calcium hydroxide plus sulfuric acid, H2SO4, forms calcium sulfate plus water. So you can see the hydrogen from the sulfuric acid and the OH from calcium hydroxide, they are combining to form water. Okay. Double decomposition reaction. Then comes esterification. Esterification is alcohol and acid forms an ester. This is used in the oil and fat, soap, and making of organic chemicals. ROH. R is any functional group. That is OH is the alcohol. ROH is the alcohol. R dash COOH. R can be anything. CH3, C2H5, C3H8, etc. Right. So this form R dash CORR plus H2O. Right. And ROH plus H2SO4 forming RHSO4 plus H2O. This is also esterification reaction. Then comes halogenation. Halogenation actually could be chlorination, bromination, etc. But mostly the word halogenation refers chlorination, right? So ethylene plus chlorine forming diethylene, ethylene dichloride, and toluene. Toluene is benzene with the methyl group attached. Toluene plus chlorine forms benzyl chloride. This is also a halogenation reaction where a chlorine is getting stuck with the other molecule. Then comes hydration. Hydration is opposite of dehydration. In dehydration, we remove a water molecule. In hydration, we add a water molecule. So calcium oxide plus water forming calcium hydroxide. This is the hydration reaction because it has consumed water. Okay. So this is also used in the organic chemical and inorganic chemical. Then comes hydroformylation. Hydroformylation is also used in the organic chemical industry. Any olefin means, remember, double bond, unsaturated hydrocarbon, can form aldehyde with additional carbon. Okay, look at this example. RCH double bond CH2 with carbon monoxide and hydrogen forms RCH2 CH2. Right, so olefin is forming aldehyde. Okay, so we need to add carbon monoxide and hydrogen to the olefin for this hydroformylation reaction to take place. Then comes hydrogenation. Hydrogenation is the adding of hydrogen. So you have a functional group which reacts with the hydrogen to form. Hydrogen will add over the unsaturated double bond to form a stable hydrocarbon. Right? That is hydrogenation. Then comes hydrolysis. Hydrolysis is chlorobenzene with water forming phenol plus HCl. So remember, benzene, the ring, with the ring structure. So chlorobenzene means in one of the corners, hydrogen has been replaced by chlorine. So chlorobenzene can react with water to form phenol and HCl. Then comes hydroxylation. Hydroxylation is ethylene plus ethylene oxide, ethylene plus ethylene oxide forming this hydroxyl group, OH. Is it okay? Hydroxylation. Okay. Hydroxylation is alcohol with ethylene oxide, right? RCH2OH, ethylene oxide, forming this product. This is used for detergent manufacture. Then comes isomerization, a straight chain becoming branch chain. Again used in the petroleum. See, you get good quantity of normal butane in the petroleum refinery, but not isobutane. But isobutane is required for the alkylation reaction. So we do an isomerization reaction where normal paraffin, CCCC, become a branch chain, iso, right? So this is isomerization. I think sulfuric acid or HF is used as a catalyst. We will do it in the petroleum refining. Then comes nitration. Nitration is the cyclohexane plus nitric acid forming nitrobenzene, explosives, dyestuffs, and organic chemicals. Then you have one more reaction. This is a C3H8, right? C3H8 is ethane, right? Ethane, C3H8 with nitric acid, you get a whole complex of nitroparaffins, okay? Explosives. Then comes oligomerization. See, when two molecules combine, it is dimerization. When three molecules combine, it is trimerization. You may call it as oligomerization also. So here is a case of 1,3-butadiene. Three molecules combine to form 1,5,9-cyclododecatrine. Right, this is oligomerization. Polymerization is large number combining. Then comes oxidation. Oxidation, umpteen examples, you can see RCH2OH with O2 forming RCH2 aldehyde, right? And then 1, 2, 3, 4, butane with oxygen, right? This is forming acetic acid and byproduct, and methane with oxygen forming CH2O, right? CH8, that is what? Acetylene, right? Acetylene and water, so they're all oxidation reactions. Then comes most interesting polymerization. In polymerization, a monomer combining to form large chain. You have, say, ethylene monomer. There are two techniques for polymerization. One is the addition polymerization, and the other is the condensation polymerization. Addition polymerization, the classic example is polyethylene, monomer ethylene, combining first two monomers combined to form a dimer, then one more is added trimer, quatermer, pentamer, sexamer, goes on, and you form polyethylene. Okay, CH2N time. Then similarly, another example of addition is polyvinyl monomer, right? So this combine again with the alkene to form the product polyvinyl polymer, right? So polyvinyl monomer may form a polyvinyl polymer, and this X could be chloride. So if that is the case, it is a polyvinyl chloride, or it could be polyvinyl acetate. Okay, so addition reaction may take place, remember, by either free radicals or by the carbonium ion, right? So you have the radical based reaction or the coordination reaction using Ziegler-Natta catalyst. Remember, Ziegler-Natta got Nobel Prize for the catalyst which will produce stereo-specific polymers. I can precisely tell what should be the shape of the polymer using Ziegler-Natta catalyst, stereo-specific polymers. Addition polymerization, and also we have condensation polymerization, where a small molecule like water, ammonia, or an aldehyde, NaCl, they get knocked out for polymerization. But for condensation polymerization, it is necessary that you have what do you call the monomers should have functional group on both ends, right? Monomer should have functional group on both ends, right? So you see here you have COOH, right? So here you have OH, and when they combine, this OH and O, one hydrogen from here and one OH combined to form water, and the chain proceeds, right? So this is condensation polymerization. Another example is ethylene glycol with terephthalic acid, right? So this forms that polyethylene terephthalate, right? So this is another polymerization reaction. So we are closing down on the unit processes. We have reduction. Reduction is titanium chloride with aluminum forming TiCl4 forming TiCl3. This is used for the catalyst manufacture for polymerization. Then you have sulfonation, where benzene with sulfuric acid is forming the sulfonate, right? So that is used for dyestuffs, right? And thionation means the addition of sulfur, butadiene with sulfur forming thiophene, right? Methanol with H2S forming Ca3SH. These are classic thionation reaction. Then you have unit operation. Many names are there: absorption, stripping, adsorption, desorption, pressure swing, chromatography, distillation, in which you have batch, flash, azeotropic, extractive, reactive, evaporation, fluidization, crystallization. I'm just naming some of the unit operations that are part of any chemical technology. Liquid extraction, also called solvent extraction, right? Membrane processes, crushing, grinding, pulverizing. You have done it in the mass transfer, you have done it in the mechanical operation course. Absorption and stripping, adsorption, etc. You have done in the mass transfer course. You will be doing distillation and some more of liquid extraction, etc. in the advanced mass transfer course. So, but we will be looking at them from the application in our technology, not from the design point of view. And that's about it. So we will get back on to the next lecture in the coming Saturday. So thank you all and have a great day. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Thank you,
Oh,
sir.
fine. Thank you.
Thank you, sir.